the image magnification is going to tell you the size of the image compared to the size of the object. And so we're going to define m as the ratio of those two lengths. So if y sub I is the object height and y sub o is the image height, then this right here is our magnification. Now, one thing to keep in mind, remember that heights are negative when the height is measured below the optical axis and positive when measured above. So this means that if your image is flipped, you would expect a negative magnification. All right, so if the image height is larger than the object height, then clearly we have a magnification greater than 1. The image is bigger. We have it magnified. If, on the other hand, the image is smaller than the object, well, we're going to have a magnification less than 1. The object is actually shrunk, or I'm sorry, the image is shrunk down compared to the object. Now, as previously mentioned, if the magnification is negative, this means that the image is inverted relative to the object. Now, one thing I want to point out, that doesn't necessarily mean that the image has a negative height. It just says that the two heights are flipped relative to one another. So here we have an object which has an object height less than 0, but the image height is positive. We still have a negative magnification. All it tells us is that one of these is pointing down, the other one is pointing up. It doesn't tell us which one is which. Now, the image height isn't the only way to go about finding the magnification. In the ray model, these lines of light are just going in a straight line. I've shown the 3 principal rays here. And to define where my image is, now if we just look at this pair of triangles right here, I'm going to go ahead and sketch those down here. Now what we notice is that this angle theta here is the same as this angle theta here. What that means is that the tangent of theta on the left-hand side has to be equal to the tangent of theta on the right-hand side. So the ratio of opposite over adjacent gives me this pair of equations, or this set of equations right here, which I can then rearrange to look like the magnification here. In other words, the ratio of the image distance to object distance is also going to be equal to the ratio of the image height to object height, simply because these pair of triangles are similar triangles. Now, one little change. Because of our sign convention, we need to include a minus sign in our equation for magnification, and that's simply because in this scenario up here, SO and SI are both defined as positive, whereas YO is positive and YI is negative. So to roll that in there, we have to explicitly put in this minus sign. So our magnification equation then is M is equal to YI over YO, or negative SI over SO, and that minus sign then will give us the same result for both of these. Now here's a question to ask. Where is the magnification equal to 1? In other words, where is the image the same size as the object? Now I should be a little bit more careful here and say negative 1 because I'm looking at a flipped image. So I'm going to go ahead and sketch my system. This is the part of the visualization stage. And then for planning, I have 3 key assumptions I need to make. First off, we're using the ray model of light. Secondly, we need to stick to the paraxial approximation, where the angle that the light rays make relative to the optical axis is much, much less than 1. This allows us to use the thin lens equation. We're also going to assume the thickness of the lens is much, much smaller than any of the relevant distances involved in the problem. So again, we can stick with the thin lens equation. Now I've listed out my knowns and unknowns, and I've really defined them in detail. This is a good habit to have. You don't need to do this all the time, but it is sometimes helpful. The only 2 equations that I really need are the equations for the magnification and the thin lens equation. So we're going to go ahead, and if the magnification is -1, then I can plug that into my magnification equation and find out how SI and SO are related. And in this case, SI is equal to SO. The two distances are the same. Now I want to figure out what exactly is SO in that case. So going to the thin lens equation, I'm going to go ahead and solve that for SO. And we end up, after a few steps, with this equation right here. You'll notice that this looks very similar to the equation for the image distance as well. If you swap out O and I, you still get the same equation simply because SI and SO appear in the same form in the original equation. All right, so then I'm going to go ahead and plug in the fact that SI is equal to SO in this equation here to give me the next guy. And then I'm going to go ahead and solve that for SO. So multiplying that term up there gives me this. And after a few more steps, we find that the object distance is 2f. In other words, when the object is located 2 focal lengths from the lens, you expect the image to be inverted but the same size as the original. So to evaluate whether or not my answer is reasonable, well, first off, I know that the distance, the object distance, has to depend on the focal length only. And this is because the focal length really is the characteristic length of the lens. Anything that's going on with the lens, distance-wise, we expect to relate back to the focal length. That's what sets our length scale. Additionally, I have actually seen the experiment, and I know that the magnification is 1 when we are sitting at twice the focal length. So based on these two facts, I feel that my answer is in fact reasonable. So just a couple of points for your own thought. Is it possible to have a non-inverted image with a magnification of 1? If so, where would that object need to be located? And if not, why isn't it possible? Another thing you might want to do is see if you can prove that the magnification is greater than 1 for objects that are between f and 2f, and that the images are shrunken when the object is between infinity and 2f.